Hello and welcome to PicMig's COM-HPC Mini Academy, a 2-hour virtual event during which we'll introduce you to the latest form factor industry standard from PicMig in PicMig's long line of computer on module technologies. I'm Brandon Lewis. I'm co-marketing officer at PicMig, and I'm joined today by Christian Eder, director of market intelligence at Congatec, and also the COM-HPC technical working group chair, as well as Matt Burns, who is global director of technical marketing at Samtec. So before we begin today and dive into some of the great technical information we have about COM-HPC Mini, we're going to do a brief overview of the entire session or group of sessions. The first one is this one, which will be about the COM-HPC Mini standard and what's new since it was released back in 2021. After this session, we're going to introduce you to the newest member of the COM-HPC specification family, the Mini, which makes the high-performance computing standard applicable in mobile and battery-powered applications, among other things. After that, Peter Hunold of Contron is going to walk us through the COM-HPC Mini Carrier Design Guide, and that'll help you accelerate your designs. And then finally, we're going to be having a multi-vendor panel of experts who will reveal their thoughts on the future of COM-HPC, COM-Express, and more. Today's session is going to consist of approximately 25 minutes of presentation, after which we'll transition into the second session of today's event. So be on the lookout for links in the chat and on screen that will direct you into that session. We'll field any questions you may have during these and subsequent events and answer all of them in the panel session at the end of the 4 sessions. That's going to be at 15:30 UTC, so you want to stick around and make sure that you get perspective from our industry leaders. So before we dive in, I just want to make sure that everybody has a feel for the audience viewing console. The first thing you're going to notice, of course, is the big presentation slides, and then, of course, video of me and the other presenters. If you need to adjust the presentation viewing interface, there's a button that says display. Click that icon from the bottom navigation, and it'll prompt you to either enter picture-in-picture or full screen mode. The next box you're going to see is a large chat box on the far right of the viewing window. You can use this to interact with other event attendees by typing your message into the box and hitting enter, or selecting the paper airplane icon with your cursor. The chat area is distinct from the questions tab, you'll notice, and you can navigate to that tab on the far bottom right, just next to the chat icon. If you select the question icon, it'll pop up a new interface that prompts you to ask a new question. Click that, then type your question for the presenters into the pop-up window and click the send question button below it. We'll address as many of these questions as possible during the closing panel session. But if you have questions related to the webcast platform operation itself, you can submit those and we'll get to you right away. Another option, if you're experiencing technical difficulties, is the help icon in the far bottom left of the navigation. Select that, it'll open a troubleshooting guide. It'll have you fully engaged in no time with a bunch of quick fixes. Some other items of note are the react button, which allows you to emote in response to cool or interesting content, and the share event button, which is in the top right of your interface, that will let you share the links to this webcast with your colleagues and professional network. A final item of note is that all PicMig webinars are copyrighted and may not be recorded without prior written consent. And so now that the lawyers are all happy, we can get going, and I'll hand it off to you, Christian.
Thank you, Brandon, for the nice introduction. So as mentioned before, I'm going to talk about COM-HPC. What else, of course? I try to give a quick overview and focus on what's new, and also stronger focus on the COM-HPC Mini, what's on there. So as mentioned before, I have the honor to serve as chairman here for the PicMig, for the COM-HPC committee, so for quite a couple of years for now. And I'm director for market intelligence at Congatec. So, but let's start into the details here. Let me start with an overview. What is a computer module? What's the concept behind? So at the end, it's a separation of the standard core functionality of a PC, more or less here, to put this to a module and to put everything which is application or customer specific to a customized carrier board. You see this carrier board has some crazy cutouts, whatnot. Everything which is specific is integrated in there. all of those computer module concepts also feature a thermal interface called the heat spreader, which goes on top, which means with this, it's a standard to the bottom, to the carrier board, where the connector, the pinout are standardized, and also to the top side, where the heat must be transmitted to the system's cooling. Overall, this separation is to have a standard, which is exchangeable, and everything customized, which goes around. So that's the logical alternative if you have special requirements here. So you might do a, let's say, chip-based design, or you might do a module-based design, which is by far easier. So it's a lot of benefits if you choose for a computer module design. Of course, it's less complex, it's faster time to market, so it's cheaper from development cost. It's scalable, which means the modules are available in the same standard here, from low end to high end, from older to newer to next generation. It's completely scalable into the future. And of course, it allows to focus your engineering efforts here to the system features, and you don't have to work into the details of the chips itself. You can react much faster to trends, to changes in the markets. We all know things are changing, and you can minimize inventory cost, and last but not least, second source philosophy. Of course, you're not depending on a single supplier. Those open standard modules are available from multiple vendors, and some of those are here on the panel by today. So overall, you see, it's a lot of advantages and a lot of different standards here. Open standards, it's not a complete list. There might be some more, but those are, from my point of view, the most important ones. So COM-Express, which is in place since 2005 or so. So there are different versions of that. COM-HPC is the newest one, which scales up. You see just from the amount of real estate, from the size, it's a different performance class. We'll talk about this, of course, in detail. And from the low-end side here, the SMARC module, it's also a standard, which is not PICMIC, but open standards are everywhere. And SMARC, COM-Express, and COM-HPC, I believe those are the most important ones. It's not a new idea to have an open standard computer or module, and I did a little exercise and did some calculations here. You see here also starting from the very left, it's ETX. Maybe even before there was DIMPC, maybe that was the first open standard module concept. But the performance levels, which is on the C-axis, is on a logarithmic scale, which means ETX had a, let's say, I/O performance. If you calculate all interfaces and sum it up, of course, it's a theoretical number of something in 500, 600 megabytes per second. And this went up over time. And now with COM-HPC, we're in the range of, let's say, thousands of megabytes actually here. So it's tremendous growth. So, and it's doubling the performance almost every 3 years. There's a doubling of the I/O performance. So that's how technology changes and how performance levels changes. It's not just the CPUs, it's also the I/Os which are important. But focusing here on COM-HPC, as I mentioned, a quick overview. The smallest one, which is in focus today, is the Mini. So it's only 95 by 70 millimeters, and it scales up to ABC. That's typically the client sizes, which means the pinout has more, let's say, user interface things like video, audio, etc. And the server sizes, which are more tailored about a high amount of Ethernet interfaces, but no audio, no video interfaces, but voice nets and much more PCI Express lines. So this defines the scale. And you see, it's extremely scalable from the Mini to the server and to the large server sizes. It's a big thing. Starting here with the server here from top down, high performance, see large sizes. the COM-HPC standard even defines platform management, IPMI Redfish, a subset of this to be sufficient to control edge servers located somewhere as a rough edge, but without the burden having to do a complete IPMI implementation. It's just a subset which is defined in a dedicated specification. It's platform management spec for COM-HPC, where it's easier to implement that for the module vendors and also for the users. It supports up to 64 PCI Express lanes, and Gen 5, it's not the truth actually. I found a bug here. It was updated even to Gen 6, but we hear later on from Samtech about PCI Express Gen 6 and the impact on that. It does support up to, let's say, 1 terabyte RAM. It does support the 25 gigabit Ethernet lanes and quite a lot of those. And it has 800 pins, so a lot of headroom here to transmit energy and, of course, to transmit fast speed of data. While the client typically is slightly smaller, so its size is A to C, it has less PCI Express lines. It's, let's say, 48 lines, also Gen 6, of course. And it does feature rich audio and video interfaces. Lots of screens can be connected, and multiple channels of audio output are there. We come to the details later on. Again, also 800 pins, but let's say the distance between that two 400 pin connectors is slightly different to the server, so cannot be mixed that easily by accident. Less Ethernet, but still featuring the 25 gigabit Ethernet lanes, which is important. And it does support, just as an example, USB 4, and it's also PICMIC standard. The latest size which was introduced was the Mini. It's much smaller. It only features one connector, 400 pins, let's say half amount of the client, but still have a lot of features here, like 16 PCI Express Gen 6 lanes and 2 Ethernets, USB 4, of course, everything which is state of the art. Of course, we had to be careful when defining this standard. 400 pins is a lot, but not enough to break out everything. We have to be clever to find a good combination of which features to bring out. This ended up in having some options for some pins. I will explain this later on. Just for your reference, that's a quick overview of the interfaces. A lot of things are similar, but there are some differences in details. That three pin-out types are not completely compatible one to the other, which means it requires a different carrier board for the Mini, for the client, and for the server. So there are a lot of similar feature set, but it's not exactly the same. So at the end, you cannot scale across those. You have to find your way here for the carrier board, which pin out to support. Of course, it's not the first standard here, COM-HPC, here on which defined a Mini form factor. Also, COM-Express defined a Mini form factor, and let's compare those two. What was there? On the left-hand side, you see the COM-HPC size with 70 by 95 millimeters, while on the right-hand side, the COM-Express Mini is 55 by 84 millimeter. Much closer here to a credit card size. COM-HPC is slightly larger. So just in square millimeters, it's 43% more. Still small and tiny, but it was defined by the higher performance levels. The chips need more real estate. We need more real estate also for the cooling, for the higher performance CPUs. Actually, this was the minimum which the engineers really did a closer look. I tried to make it smaller, but reality proved that this is the right size here to get the right performance levels on COM-HPC Mini. From the stack height, so there are different connectors here on COM-HPC for a stack height of 10 millimeters or 5 millimeters in comparison to COM-Express, with 8 millimeters or 5 millimeters. So the smallest stack height for COM-HPC Mini is slightly less than it is on COM-Express. It's 18 millimeters for the 5 millimeter connector and just 15 millimeters for the also 5 millimeter connector combination here on COM-HPC. This 50 millimeters is counted here from top of the carrier board to the top of the heat spreader. Of course, it also the thickness of the carrier board must also be added at the end, and if required, the cooling interface. But quite often the heat spreader is, let's say, mounted to a chassis, to the system cooling, to make it, let's say, passive cooled, makes it quite easy. Bring me to the point here, how to mount a heat spreader. So sometimes it causes confusion. Let me explain it. So there are two versions of the heat spreaders usually available. So one is with through hole, the other with threads. So, but what's the difference? On the left-hand side, for the top mounting here, you need to have a through hole, and the carrier board does have standoffs with threads in order to really provide the right pressure to do the right conducting. If you want to do it the other way around, like mounting the whole stuff here directly to a chassis or so, the other way might be also an option to have the threads at the heat spreader, but then you need to have the through holes here on the carrier board. That's a two combination, depending on your physical implementation of the solution. Just to clear this point up. On the feature set, so this plus 82% is just based on the pin count, 400 pins by 220 pins. Of course, more pins also means more I/O, more functionalities. So, and just for this quick overview, on the gray tabs, you see you'll see the more details. But overall, Ethernet, COM-Express only had one Ethernet. With COM-HPC, we have two, and the option for another two, which are multiplexed with PCI Express lines. So the asterisk means it's there's some multiplexing behind. PCI Express, it's 4 against 16. So USB 4 was not in place when COM-Express was defined. We can support up to 4 USB 4 interfaces on COM-HPC on the Mini. But this also does some multiplexing. This double asterisk means that's a multiplexing with the DDIs and the USB 3 lanes. I'll come to this later on. There are some more GPIOs, and functional safety dedicated pins are defined for COM-HPC. Also, we'll have a slide about this one. What the pin sharing is just recognized or just mentioned. The PCI Express lanes, 16 in total, are grouped in a, let's say, a lower and higher groups. The higher group, the lanes 8 to 15, are typically used for NVMe, for, let's say, high-speed interfaces, whilst the lower ones are more for the IOs. Some of the lines might be used as alternatively for Ethernet. So the lanes 2 and 3 can be implemented, and that's vendor specific. With some chipsets, it might also be switchable, whatnot, with SGMII, which means that's a serialized Ethernet implementation. So this allows the possibility to implement up to 4 Ethernet channels without external chips, of course. So that's the or external Ethernet controllers. You can always attach these Ethernet controls on PCI Express. Lines 6 and 7 might be used, or may be used, so that's spec language, as SATA lanes. I don't believe that SATA has that much of importance nowadays, as we have the NVMe, the PCI Express attached to devices, which are much faster, but there's still the option for a certain backwards compatibility. About the multiplexing for the super speed lanes, so there are different configurations defined. In total, we have 8 super speed lanes, which are shared between the digital display interfaces, USB 3 lanes, and USB 4 lanes. So you see here all combinations are possible, which means It's not all combinations. Let's say some practical combinations are defined. It's up to 5 configs. And I believe something like a configuration 2 is the one which makes most sense nowadays, but there's scalability. A pure USB 4 implementation like config 5 might not make sense today, but of course, the standard must be future-proof. And these 8 lanes can be multiplex. It's clearly defined. When selecting your carrier board module combination, make sure that the configurations are compatible. So it's a kind of subtype, if you want to call it that way. This allows really for maximum use of the limited amount of pins we have available. MIPI CSI, I have to say, camera interface is becoming more and more important on all platforms. So, COM-HPC is not defined to be x86 only. It can also be ARM, can be FPGA, can be whatever you might think about. And MIPI is an important interface. And just like we have done it here on SMARC, we have done it here on COM-Express, there's a flat foil connector and the placement is, let's say, proposed in the specification. The pinout is identical to the COM-Express or to the SMARC implementations, which means there's a good exchangeability or reusability of technologies which are in place already. So up to, let's say, 4 MIPI cameras, or each connector has 2 channels. So up to 4 MIPI cameras might be connected by this flat foil cables. A word about the power consumption, of course, size and power consumption go along. The server is the most power hungry, and the server chips are most power hungry too. So we can bring up to 358 watts across the connectors. That's including some derating of the connector and so on. We do have 28 power pins, and at 12 volt fixed, or let's say we use for the maximum power consumption the minimum 12 volt minus this 5%. At 11.4 volt, we can have this more than 300 watt across the connector. For the client, there's a wide range input, 8 to 20 volts. And of course, at the 8 volt level, we can bring up to 250 watts across. And Mini has a slightly different definition. So it's again 8 to 20 volt, but it has a reduction of power pins. And overall, we have less pins, less real estate, we don't need that much power, but still more than 90 watt can be transmitted by the connector. And as a, let's say, legacy thing, we did remove the standby power voltage for the Mini. No standby power voltage is defined, is needed. So we could release another 1 or 2 pins here for better use. Already mentioned functional safety. That's a complicated thing, but COM-HPC is prepared for. The Mini, but also the client and the server definitions feature a total of 12 extra pins, which can be used to implement functional safety. So it's an indication here to a carrier board, where typically there must be the functional safety controller. And on the module, yes, there can be a safety island implemented. The interface contains mainly about an SPI interface with an alert pin and some status lines, which are power, the status power off, okay, not okay, or a reset, to really clearly indicate with these 2 pins what is the status here of the module. And then some error messages or error indications here, like a thermal shutdown if the CPU went hot, or it's not, or it's about to become really hot. So if it's throttling, for example, then there's another event. Or in general, if there's any other catastrophic error, it will be indicated, which means if any bad error is indicated, then the functional safety controller on the carrier board can react accordingly and shut down the functionality of the functional safety relevant functions of the system here. That's completely prepared. I have not yet seen implementations yet on this, but it's prepared and it will happen over time because functional safety is important. If we think about all this autonomous functionality on robots, on vehicles, whatnot, that's relevant for that, and we will see more of that. Another point is 25 gigabit Ethernet. Here's a quick overview about the Ethernets we're supporting here. So the typical N/T can scale up with some chipsets, even up to 10 gigabits in the meantime. On type 10, we have just one on COM-Express, type 6, type 7, all just one Ethernet. On type 7, we have another 4 KR interfaces, which means 10 gigabit Ethernets. But that's it. It's not that much. Looking to COM-HPC, on the Mini, we can have up to 4, again, with some multiplexing. On the client, 2 N/T and 2 25 gigabits. That's wrong on this table. Sorry. Reviewing slides didn't work that well. And on the server, we do have up to 8 25 gigabit, which means with 8 25 gigabit lanes, you can implement 2 times 100 gigabit. So you can bundle those lanes here into any kind of different standard, into fiber, into copper. There are a lot of possibilities how to do this here on it. So you see overall a lot of I/O performance, which does happen here on PIC-MG. And I/O performance is the keyword here for Matt. So the performance is limited by the connectors, and with the PCI Express Gen 5, Gen 6, we have lots of headroom. And Matt will tell much more about that.
Thank you, Christian. That was a great segue. And we appreciate the opportunity to not only work with you and Brandon and the team, but thanks also to our listeners for joining us. So the first thing that we wanted to do is just provide some additional details for the connector selection on COM-HPC 1.2, COM-HPC Mini, as well as some of the additions that were made to some of the legacy interconnects. So just as a brief reminder, the COM-HPC connector, it's very high performance. This connector, the design on this connector started 5 years ago, and we were targeting PCI 5, but as the work on COM-HPC has started from, COM-HPC, when it was originally released in 2021 to where we're at now, it became evident that there's a PCI 6.0 or PCI 6 Gen 6 performance of 64 gigabit per second PAM4 requirements. And we'll talk about that here in just a moment. But why is there such interest when it comes to PCI Express? And Christian mentioned this briefly, but before we dive into that, wanted to give a little bit more detail in terms of why PCI Express is so important. But we'll talk about that once we talk about the connector. So just some additional details about the COM-HPC connector. It's a 400 pin or four row by 100 column connector with a BGA mount. It's a very small form factor. The spacing between rows is 2.2, 2.4, and 2.2 millimeter row between the pitch. We'll talk about that, why that's important in just a moment. The pin-to-pin pitch is 0.635 millimeter, and you can see that the connector itself has a very small form factor or PCB space, roughly 70 millimeter by 9 millimeter time to stack height. We do have 2 stack height options. There's a 5 millimeter stack height, which allows for a very thin envelope for panel PCs or mobile applications. The 10 millimeter stack height enables increased density so that you can have components both on the bottom side of the COM-HPC module as well as components on the top side of the carrier card when the modules are stacked on top of each other. And those same benefits are the same through all 5 form factors, COM-HPC server and client, as well as the new COM-HPC Mini, which we'll detail a little bit later this afternoon. We have added one additional feature within the COM-HPC 1.2 spec. We have added one additional feature to the connectors. COM-HPC 1.0, COM-HPC 1.1 did not have weld tabs. However, because of the increasing feedback that we've heard from implementers of COM-HPC, adding this new weld tab really enables increased ruggedization and reliability within the system. And because of the performance capabilities that Christian's so expertly defined, COM-HPC is finding homes that may have been unanticipated. So having this increased performance, or this increased ruggedization, this increased reliability is a necessity. So by adding this weld tab, that accomplishes a few things. One, it transfers mating and unmating forces into the mechanical support. So instead of that being all on the solder attachment between the connector and the PCB, those mating and unmating forces are distributed through the weld tabs on both sides of the connectors, both on the carrier and also on the modules as well. Some people have asked, well, doesn't this mean that I have to completely redesign my system? And to implement the weld tab, yes, you have to redesign the PCB footprint, which we'll talk about here in just a second. But if you already, if an OEM or an implementer already has a COM-HPC carrier card designed, and you only want to update the module, the weld tab version of the connector will still mate with the non-weld tab version of the connector, because it's the electromechanical interface has not changed. So it does maintain backwards compatibility when designing a module with a weld tab versus a carrier without the weld tab, or vice versa. If you have a module that doesn't have the weld tab, you design a carrier card that does have the weld tab, they'll intermate without problems. The new modules will support all carrier designs, which is basically the point that we were making. So the changes, what changes are necessary? These are the updated module connector and carrier connector PCB footprints. So you'll see in the highlighted areas that both on the module connector, we've added 2 additional drill holes on the connector footprint to enable using the weld tab. The same thing on the carrier card. So the only change, again, is 2 additional drill holes on the carrier card, 2 additional drill holes on the module, and you can enable these next generation connectors. So, again, Christian talked a lot about how PCI, COM-HPC has done a really nice job of adding PCIe connectivity throughout the system. And when originally conceived 5 or 6 years ago, the intent was to enable PCIe 5.0 performance. But since then, PCI SIG has released the PCI 6.0 version of the PCI Express specification, and that does a couple things. One, it doubles the speed of PCI Express from 32 gigatransfers per second to 64 gigatransfers per second. It uses additional encoding. We go from an NRZ to a PAM4. It also adds CRC, FEC, and some additional features to make the transition from 32 gigatransfers per second per lane to 64 gigatransfers per second per lane simplified. Now, when the original COM-HPC spec was created, there was a lot of SI work that was put forth to enable PCI 5 capability, but we want to show how implementers right now can leverage the SI hooks, if you will, within the COM-HPC spec and within the COM-HPC carrier design guide to design future-proof systems for PCI 6. The reason I say PCI 6 future-proof is the fact that we're still waiting for x86 CPUs, other solutions, other compute engine solutions from the semiconductor providers to have native PCI 6 support. We're not quite there yet, but we're coming. But as implementers, we have to start to design for those standards. So how has PCI 6 capability been enabled within COM-HPC to date, and also going forward? That's what we're going to talk about here for the next few moments. So one of the subcommittees within the COM-HPC technical working group was a group of companies focused on signal integrity performance for all the protocols that Christian talked about: Ethernet, MIPI, PCI Express, et cetera, et cetera. And the signal integrity design work is captured within the COM-HPC specification and also the COM-HPC carrier design guides. what we're going to do for the next few moments is extract some of that detail to talk about how COM-HPC modules, whether that's a client, a server, or a mini, currently can support PCI 5, but also how there's a roadmap to PCI 6 when that's enabled within the chipsets available from the semiconductor vendors. So what does that mean? The SI team went through a step-by-step process to, in essence, validate this performance. PCI SIG determines the loss budgets for high-speed interfaces specific to PCI Express. PCI Gen 3 has a loss budget of about 24 dB point-to-point, silicon to silicon. PCI Gen 4 is about 32, PCI 5 is 36, and PCI 6 is 32. So using those loss budgets, we can perform a loss budget analysis of how that signal channel applies to COM-HPC channels, which we'll get to in a second. So looking at each of the components from an SI standpoint, we build 3D models of the connectors, the PCB, module and carrier cards, plus the differential via and strip lines within the carriers and also the modules itself. We build those models, we simulate the models, or excuse me, we build those models, we build the channels, we simulate the components, we simulate the channels, and then the result of that work, both the simulation and the testing are within the standards. So what does that mean for COM-HPC? Well, remember when we talked about the connector, we talked about 2.2, 2.4, 2.2 row spacing. That was one of the design decisions that were made to enable high-speed performance, not only through the connector, but also through the breakout region, or where the signals break out when they're attached either on the client, on the modules, or on the carrier card. So by having that increased row-to-row spacing, we're able to use a ground signal ground pinout for the high-speed signals, PCI Express, Ethernet, et cetera. That's a good design practice for high-speed performance. We're also able to add more ground vias within the system, which helps to minimize crosstalk and eases differential routing for high-speed traces. So what does that mean for the performance of the system? Well, when you look through the PCI SIG specs, we only have time to look at two bits of data. But when you look at the PCI SIG specs for insertion loss and return loss for a PCI Express connector and a PCI Express connector versus the breakout region when it's attached to a PCB, for insertion loss, you get roughly 2 dB. So when looking at what we have for COM-HPC at 16 gigahertz, which is the Nyquist frequency for PCI 5 and also for PCI 6 since it uses PAM4, we see an insertion loss for both the 5 millimeter connector and the 10 millimeter connector well below the mask at 2 dB. So that tells us that the PCI Express connector will work at the COM-HPC connector will work at both PCI 5 data rates and also PCI 6 data rates. Similarly, when looking at return loss, if you look at the PCI SIG specification for both PCI 5 and PCI 6, they define a return loss for a PCI Express connector and a breakout region. We're analogously doing that for COM-HPC of roughly 10 dB at our frequency of interest. So again, looking at 16 dB, we have a return loss of beyond 10 dB, both for the 5 millimeter and the 10 millimeter solution. So that's for the connector between the carrier card and the module. But what about the system? Well, again, we take the components going from the semiconductor package all the way down to the transmit package, all the way down to the semiconductor receive package on the PCB. We simulated the channels, tested the channels, and the results that we've received so far confirm conformance for PCI 5, but also give us confidence for PCI 6. So what are the end results? We looked at two use cases within the SI version of the COM-HPC spec, and what we see is there's a version where you have the carrier card, the module on a carrier card with a transceiver on the carrier card, and then in another use case instance, you have the carrier, the CPU module, again, server client COM-HPC mini, the carrier card, and a additional daughter card. This could be PCI Express, whatever the case may be. So within the COM-HPC spec, we can see that depending upon the PCB material used, depending upon the length of the traces, for each of the versions of PCI Express, PCI Gen 3, PCI Gen 4, PCI Gen 5, there's a max trace length from the CPU to the connector and from the connector to the piece of silicon on the carrier card. So again, all the work has been done to show that PCI 5 works. This points forward to the fact that PCI 6 will work within COM-HPC. Samtech has simulated the COM-HPC connectors we have at data rates of up to 112 gigabit per second. And as time goes on, more work will be done and more signal integrity results will be released for PCI 6.0 capability within COM-HPC.